Hi there. It is time for section 2.1 in Precalculus 1. This is Professor Shannon Gracie. We are working out of the Precalculus Enhanced with Graphing Utilities text by Sullivan and Sullivan. Today we are going to cover the initial things to do with functions. So you can read the goals here with the bullet points, and let's go ahead and move on to our warm-up. So we need to find the values of x for which this rational expression is undefined. And here, if you think about fractions, is it okay for there to be a 0 in the numerator or denominator? Well, one way to think about this is division is counting how much of one quantity is in some other quantity. And if you have 0 in the numerator and you have something that is not 0 in the denominator, then, like for example, 0 divided by 2, you'd be counting how many 2's are in 0, which of course would be good, 0. But if you look at the converse, which is how many zeros are in 2, which would be 2 divided by 0, would you ever stop counting, right? There would be infinitely many zeros in 2. And I don't know about you, I love math, but that is not what I'd want to keep doing forever. So, 0 in the denominator, not okay. 0 in the numerator, okay, unless there's a 0 in the denominator. When you guys are with me in calculus, what you'll find out is if you get 0 over 0, that is an indeterminate expression, and we will be working more with those kinds of things later on in your math life. So for the time being, we're going to figure out when this denominator here is 0. So, and we will exclude that value. So if you want to say 2x squared minus x minus 10 is not equal to 0, that's okay. And I think I've shown you, a bit about factoring. So let's review the quadratic formula. We basically want to figure out when x is not equal to, well, we'll figure out what will zero out the denominator, and then we will exclude it. So if we use the quadratic formula, basically the quadratic formula is when you have ax squared plus bx plus c equal to 0, where a, b, and c are in the real number system, then x will be equal to the opposite of b plus or minus the square root of b squared minus 4ac, all divided by 2a. And so in this case, x will equal the opposite of negative 1 plus or minus the square root of negative 1 squared minus 4 times 2 times negative 10 all over 2 times 2. And we will have x is equal to 1 plus or minus the square root of. So we have positive 1, minus a minus is plus, so 4 times 2 is 8, times 10 is 80. So we'll have 81 under the radical, all over 4. So x will be 1 plus or minus 9 over 4. So solving, we will have x will either be 1 plus 9 is 10. 10 divided by 4 is 5 halves. And 1 minus 9 is negative 8. Negative 8 divided by 4 is negative 2. So those are the values that we would want to exclude. So x cannot equal to negative 2 or 5 halves, because that will yield a quantity of 0 in the denominator, or a value of 0 in the denominator. All right. So now we get into determining whether a relation represents a function. So when the value of one variable is related to the value of a second variable, we have a surprise, surprise relation. So a relation is a correspondence between two sets. So if x and y are two elements in these sets, and if a relation exists between x and y, then we say x corresponds to y, or that y depends on x. And we write this notation. X corresponds to y. So x arrow y means x corresponds to y. So there's different ways to express relations. You can express relations as an equation, which is common. You can express them as some sort of a graph. Sometimes it's a graph of ordered pairs. Or you could express them as some sort of a map. So here we have a correspondence. So, a car has, hopefully you know this, has 4 wheels. A motorcycle has 2 wheels, and a boat has 0 wheels. So this is the map. Car maps to 4. So 4 is the image of the number of wheels for a car, and so on and so forth. So a person could actually express this as a set of ordered pairs. You could express this as car, comma, 4, so type of vehicle, comma, number of wheels. We would have motorcycle, comma, 2, and then we would have boat, comma, 0. And the set brackets on the end designate that these are all in the same coordinate plane if you were graphing them. Now, the domain is the set of all possible inputs. So in this case, the inputs, not domains, my bad. The domain will be the set of inputs, which are car, motorcycle, and good, boat. And the range will be the set of all possible outputs. So we had outputs were the number of wheels. So putting in them in ascending order, we'd have 0, 2, and 4. And there we go. We found the domain and range of this relation. So let's go into defining a function. So that capital X and capital Y represent two non-empty sets. So something is in the set. Don't be too freaked out by non-empty. A function from X into Y is a relation that associates with each element of X. Exactly one element of Y. So let's consider the graph. This is the graph of y equals x squared. So let's bring our little graphing calculator up and go to our y equals screen. I'm going to clear these out. And so here we go. If you start with considering the set of the input values being the set of real numbers and the output values being part of the set of real numbers. And if you think of this equation, you've graphed it before. Y equals x squared. This is a good example because with y equals x squared, do you see that we have all possible input values? So you can put whatever the heck you want in for x. But what do you think for y? As you look up and down here on this equation, right? The up and down values represent the possible range values given that x equals some input value. And you see that we're all above the x-axis. So what you have, they always make these funky little kidney-shaped things, right, for these deals. So let's just suppose we have this capital X, and capital X we could pick from any real number, right? And if you pick, let's just pick some specific X values. Let's say X is -2, +2, and I don't know, how about 0? And let's take a look at these output values, So from the output values, you could potentially have all real numbers for y. But, you don't have to have you could have a subset of these, right? Because if you look at this graph, which we said was y equals x squared, do you see you're only going to have the positive whole numbers and 0 for your output values? So you can actually do something called a map. So you can map these values here and you get something called an image. This image here, if you plug -2 in, gives you a result of +4. Guess what? +2 also maps to +4. 0 maps to 0 because 0 squared is 0. But, the set of real numbers contains things like, hey, -1 and -4. But there's going to be no mapping there because based on this definition here of this relation, we're going to have positive outputs or 0 outputs for y, given that we're squaring each input value. So, what does this all mean? It means that your range can be a subset of the potential real number system, which y represents in this case. But x has all possible values, right? Any real number you can plug into this and you'll get a result. Even if you plugged in -1 million or hey, -1 bazillion if you're making things up, you're going to get an output of a positive number. But here, the range values are a subset because the range depends on the equation and on what you put in to the equation. So the range values will be from 0 to infinity on this this particular relation. Okay. Now, one thing I wanted you to notice is if you plug in -2 into this equation, this relation, you will get a single output of 4. It is true that if you plug in 2, you will also get 4, but 2 does not map to anything else. So this means that this equation here, this relation, happens to be a function because each x value has exactly one y value that it maps to, and it passes something called the vertical line test, which we'll get into more later. All right? So let's move on down and fill this out. Functions are often given in terms of equations rather than as sets of ordered pairs. Not that you can't have a set of ordered pairs, but more commonly in pre-calc you're going to see equations. So consider this equation here. This models the position of an object in feet dropped from a height of 500 feet after x seconds. The variable y is a function of the variable x. For each value of x, there is one and only one value of y. Make that nicer. The variable x is called the independent variable. Independent. Because it can be assigned any value from the domain. The variable y is called the dependent variable because its value literally depends on x. When an equation represents a function, the function is often named by a letter, such as the script F, G, and H, or capital F, G, or H. Any letter can be used to name a function. The domain is the set of the function's inputs. And the range is the set of the function's outputs. So these outputs are often considered the image of the inputs. If we name our function f, the input is represented by x and the output is represented by f evaluated at x. The notation f evaluated at x can be read f of x or f at x, which is often what I'll say so that we don't confuse f with times. So we may rewrite y equals negative 16x squared plus 500 as f at x is equal to negative 16x squared plus 500. Now, let's evaluate our function after 1 second. So we'd plug in 1 for x, and we would have f at 1 is negative 16 times 1 squared plus 500, which would give us, well, 1 squared is 1, so we'd have negative 16 plus 500, which is 484. So what the heck does this mean? This means that after 1 second, the object is 484 feet above the ground. So, I mean, an obvious application here would be missiles, right? You know, you need to know the trajectory of a missile if you are firing it at something. This works also for a baseball, right? If you do the trajectory of a baseball, it'll go, if it's hit up at all, it'll go up a little ways, but it drops eventually because of gravity, right? So that's also modeled by a parabolic function. So let's take a look at this guy here. Determine whether each relation represents a function, and then identify the domain and range. So let's do our typical plus or minus 10 for our scale. This is x and this is y. And what we have here is we have a set of ordered pairs. So let's plot these. Okay, so we have negative 6, 1. So 1, 2, 3, 4. I'm losing it. 1, 2, 3, 4, 5, 6. And then 1. And we have negative 1, 1, 0, 1, 1, 1, and 2, 1. So in something like this, you've been given a list of ordered pairs, so you do not connect the dots. Believe it or not, this is the graph. Now, tell me what you think. Does each input value map to exactly one y value? Well, yes. -6 only goes to 1. It doesn't go anywhere else. So this is indeed a function. So this is a function. So yes, this is a function. This relation is a function. That's part of it. And the domain is going to be the set of input values. Now we don't want to repeat any input values, and they don't seem to repeat. So let's put them in ascending order, all the x values. And then what about the range? Good. You only have a single range value, right? The range is 1. So this is the complete result. Oops. Let's do this nicer. This is the complete result for this problem. And if you need these labeled, this is at 1, 1, and this is at 2, 1. All right, so let's take a look. Why don't you pause the movie and give this one a try and see how you do. Okay, so I'm going to check how you did. I'll do the regular scale here, plus or minus 10 on each axis. And let's do our graph. So we have an ordered pair at 3, 3. We have an ordered pair at -2, 0, 4, 0, and -2, 1, 2, 3, 4, 5. Okay? And again, we're not connecting any dots. I mean, how the heck would we connect them? We don't know which way to go. So here, you tell me, does it meet the definition? Where's the problem child? Good, there's an issue here, right? Because when you're at x equals -2, do you see that you have two different outputs? So this is not the graph of a function. So it's a perfectly fabulous relation, but it doesn't happen to be a function. So we're going to say not a function, but we can still give the domain and range. The domain is going to be the list of numbers. I'll put it in ascending order. -2 was the smallest. I'm looking at these x values. And then we had, what do we have? 3 and 4. And the range will be the list of the y values without repeating. So we have 0. Actually, -5, I think, is this. Uh-oh, my apologies. I did +5. We'll have the same result, but this is down at -2, -5. So 1, 2, 3, 4, 5. Here we go. So again, same result, just a different location. So we have our range is at -5 is the minimum, and then we have 0 and 3. Okay. So moving right along. Find the indicated function values. So here we go. Function notation is really awesome because with function notation, you don't have to say, oh, evaluate, y at x equals some number. This 4 tells us that we are plugging in 4 wherever we see an x in the original function. So this will literally be negative 4 squared plus 4 times 4. So the input value is 4, which I highlighted. So this will give us a result of f at 4 is the opposite of 16 plus 16, which gives us an end result of 0. So f at 4 is 0. Good so far? Great. So now we're going to triple the function evaluated at -2. So we're still working with that same function. So this is going to be equivalent to 3 times. And then wherever we see an x, we're going to plug in a 2. So I'm sorry, we have -2 wherever we see an x. So the opposite of -2 squared plus 4 times -2. So in this case, we have -2 is our input value. And then at the end of the day, we're going to triple our result. So 3 times our function evaluated at -2 is 3 times. So -2 squared is 4, and then 4 times -2 is -8. So 3 times the function evaluated at -2 will be, so -4 minus 8 is what? Good. -12. So we'll get a result of, if we triple our function evaluated at -2, we will get -36. And you can always, go and double check. When you square a negative, you get a positive, right? So that'll assign a negative here. You make sure you copied everything right. We did. Plus 4 times -2. We get -8. That's -12. And we get -36. Good so far? You guys are doing great. Hang in there. Now, instead of plugging in a constant, we're going to plug in, it's actually a linear function, right? X plus 1. So our function is still the same, which was the opposite of something squared plus 4 times that something, right? So the opposite of our something, which happens to be x plus 1 squared, plus 4 times that something. So we will get, now I don't know if you guys remember this, how you feel about this, but when you square a binomial, if you have a plus b, the quantity squared, that results in a squared plus double a times b plus b squared. That's useful to remember. So this is going to result, our a is x, so we'll have x squared plus 2 times x times 1 plus 1 squared. We'll distribute the 4 throughout and we'll get 4x plus 4. So we'll have negative x squared minus 2x minus 1 plus 4x plus 4. And that will give us a result of negative x squared plus 2x plus 3. And let me make sure I added right. All right, looks good. So moving right along. Okay, this is one of the big dogs, all right? This is something you should be okay with working with. It is called the difference quotient, and we will learn in calculus limits. So basically, the limit as x approaches 0 of this difference quotient, not x approaches 0, my apologies, h approaches 0 of this difference quotient is equivalent to the derivative of this function. So this next area is very important. It is called the difference quotient. And in calculus, it'll look a little different. H will be delta x, which is considered a small change in x. But if you evaluate the limit as h approaches 0 of this difference quotient, what will happen is you'll find the derivative of this function, which is the slope of the graph or the slope of the tangent line at x is x. So it is important for you to be able to evaluate this expression. So here we go. Again, we're still working with the same function of x, which is negative x squared plus 4x. So in for x, we're actually going to be plugging in x plus h. So let's go over here and say f at x plus h is, and again, I'll look at this. It's late in the day for me. Negative x squared plus 4x. So we'll have negative x plus h squared plus 4 times x plus h. So this is what we are plugging in for x. And we will get a result of, using the formula shown above, x squared plus 2 times x times h plus h squared, and then plus 4x plus 4h. So we will have negative x squared minus 2xh minus h squared plus 4x plus 4h. And recall that f of x was negative x squared plus 4x. So plugging in these values, we'll have f at x plus h was negative x squared minus 2 times x times h minus h squared plus 4x plus 4h. We will be subtracting from that the function evaluated at x, which was negative x squared plus 4x. And that's all going to be divided by h. So we will have negative x squared minus 2 times x times h minus h squared plus 4x plus 4h plus x squared minus 4x, all divided by h. Now you'll see that the x squareds will zero out and the 4x's will zero out, and we'll have negative 2 times x times h minus h squared plus 4h divided by h. It's looking better now. And factoring out an h, we'll have negative 2x minus h plus 4 divided by h. So the h's divide out, and we'll have negative 2x minus h plus 4. And we're done. We've simplified the difference quotient. When you're in calculus, you'll be sending the limit as each approaches 0, and you'll end up finding that the slope of the graph is negative 2x plus 4. So it's really awesome. You can find the instantaneous rate of change of a curve at any value of x. Okay, so here we go. Find the indicated function and domain values using the table below. So here we go. So the function value h evaluated at negative 2. So in this table, the second column are the y values, the function values, and in the first column are the input values or domain values. So we're being asked for a function value when we are asked for h when x is negative 2. So you look at when x is negative 2, hey, h is good, positive 2. What about when h is positive 1? Go down here. Yes, we'll get positive 1. Perfect. Now we're being asked for domain values. For what values of x is h at x equal to 1? Well, you get function values of 1 here, right? And here. So the domain values that correspond are when x is negative 1 or 1. Okay? All right. The next example is determining if these equations define y as a function of x. So remember that though two different x values could share a y value, a single x value cannot map to two different y values. So let's check it out. Here, if I were to isolate x in each of these, right? Do you see that x would equal to 5 over y? So each x value will go to a single y value. Now this is not what we would use for graphing, so please don't get confused with that. But this tells me that this is a function. So y is a function of x, because each of these x values is only going to have a single y value as a result. So for graphing purposes, of course, you would isolate y and solve and do your graphing. But we're just determining if something is if y is a function of x. So if I were to isolate x, I would have x squared is 16 minus y squared. And then if you square rooted both sides, you would get that x is plus or minus the square root of 16 minus y squared. So basically what would happen is one x value maps to two different y values. So our conclusion is what? Y is not a function of x. Again, for graphing purposes, you would isolate y, but we're determining if y is a function of x. And so this was the best way I could see. Okay, so finding values of a function on a calculator. So there's a couple ways one could do this. So we have this function here, and personally, I think the easiest way to do this is going to be to graph the function. So if we go to our y equals menu and we clear it, and then we put in this equation, the right side of the equation, which is negative x cubed minus x plus 2, and we graph it. Now, I'm going to go ahead and zoom standard. We were on zoom square from the last section. Now, this is really cool. So you go to second, calculate, value, enter. So I'm going to say, I'm going to show you this. Paste. So the cool thing about this menu is that you can plug in more than one value. So I'm going to hit enter, and it's going to ask you what x is. So the first one, part A, says x is 4. And you see we get y is negative 66. I'm going to take a screenshot to show you. So we would say f at 4 is negative 66. And then over here, we don't have to re-enter anything, which is awesome. You just do a new value, negative 2 for x, and hit enter. And we get y is 12. So we say y is 12. So how cool is that? Technology is awesome. Okay, so next up we have dun 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 steps for finding the domain. Domain is very important in calculus because we do all kinds of things. And long story short, a function is not differentiable or integrable if the function is not, continuous at a certain value. So there's also other caveats there, but for now, let's think about continuity. So if you have a vertical asymptote or a jump or something like that in a graph, you're not going to have continuity. So we need to learn how to find domains. So you can start with the domain as the set of real numbers. If the equation has a denominator, exclude any numbers that give a 0 denominator. If the equation has a radical of even index, like the square root or fourth root of something, then you need the radicand to be greater than 0. So the expression inside the radical has to be greater than 0, which means that you exclude any negative values. So let's take a look at these examples. We'll find the domain. So here we have a square root of the quantity 2x minus 1. We do not want any negative values. So we are saying that 2x minus 1 has to be greater than or equal to 0. So if I add 1 to both sides, I'll have 2x has to be greater than or equal to 1. Dividing both sides by 2, dividing both sides by 2 to isolate the x, we will get x must be greater than or equal to 1/2. So, different kinds of notation. Set builder notation, you'd say x such that. That line means such that. It's describing what the behavior of the input value x. So x such that x is greater than or equal to 1/2. Mostly in calculus, unless you're dealing with trig functions, you use interval notation. So this is set builder notation. Interval notation basically says, hey, x has to be greater than or equal to 1/2. So 1/2 is the left endpoint, and we go infinitely to the right. So this is interval notation. So if you looked at this on a number line about x, this is what it would look like. You'd have, you know, this number line here. And suppose this is 0, 1, and 2. You would basically have right at 1/2 a closed circle, which is typically denoted with a square bracket here. And you would say, okay, anything to the right of that is a solution to this statement. So this domain is represented by this graph and these different set notations. All right, so part B, what do you think? We do not want what? Great, a 0 in the denominator. We do not want a 0 in the denominator. So if we find out what the zeros are, we can exclude them. So x squared equal to 81. If we square root both sides, we would get x is plus or minus 9. And these are the numbers that need to be excluded. So this one's a little funky, right, with the notation. It's real easy with the set builder. Unfortunately, your calculus text is going to be using interval notation. So set builder, yeah, awesome. X such that x is not equal to plus or minus 9. But interval notation, which is what you'll be expected to use in calculus, would be a little more complicated. So let's look at a number line and let's denote -9 and 9 since they were the interesting numbers. And if you think about it, so you'd have an open circle, you're excluding them. So you'd have a situation where you could be to the left of -9, you could be in between -9 and 9, and you could be to the right of 9, right? But you don't want numbers exactly at -9 or 9 for your domain inputs. So this is how we do it. You're saying anything to the left of -9 but not including, union, that middle interval, and then union 9 to infinity. So these are the domains. And this was this guy. All right. Okay, moving right along, the algebra of functions. So I just wanted to give you guys sort of a big picture idea. We'll do some of this with the graphing calculator, and we'll do some of this just by looking at the graphs. So let's take a look at these two functions. They're both okay. So let's consider these two functions. Let's graph this function f equal to 2x in green and this function g, which is equal to x minus 1 in blue. So here we go. We'll name our scale. We can use the same. So x, I'll just call it x and y for this one. 10, 10, -10, and -10. Oh, there's the one down from there. That's fine. We'll actually be changing the y coordinate, but this one is the one I was working with. This will be changed to f plus g at x. But we still have to do the initial ones. So here we are. X and y. 10, 10, -10, -10. So here we go. So f at x equal to 2x we'll have ordered pairs at 0, 0. And when x is 1, we'll be at 1, 2. And when x is 3, we'll be up here at 3, 6. Okay, so far? All right, so the blue line, so this, of course, is our f at x. The blue line, which is x minus 1, we have a y-intercept down here, so we'll have the ordered pair 0, negative 1, and our slope is 1. So for every one we go up, we go to the right 1. So our line will look something like this. Good so far? Awesome. So let me label some of these points. So we'd have an ordered pair here at 1, 2, and here we'd have an ordered pair at 2, 3, 2. So that would be 3, 2. So if we copy this, we'd have this. And of course, this is our g at x. We go down here. We labeled this already. And if we take a look at doing this by graphing, we could actually figure it out ordered pairs. I'll do this one in black. So we're summing the y values. So the input values will be the same, but the y values will be the sum of the y values of these two graphs. So we'd have an input value at 0, negative 1, because 0 plus negative 1 is negative 1. We'd have an input value at 1, 2, because 2 plus 0 is 2. We'd have an input value over here at 3 is the input, and then we'd have 6 up here plus 2 is 8. So 1, 2, 3, 8. So we would get this, this line here for our f plus g at x. Now, not everybody likes to do that looking at the graphs. So it turns out that this is the equivalence. So if you recall what the functions were, f at x was 2x and g at x was x minus 1, we would have f plus g at x is 2x plus x minus 1. And this is our f at x, and this is our g at x. So combining like terms, we would have f plus g at x is 3x minus 1. So that would be a slope of 3 and a y-intercept of negative 1. So let's check and see if we got it right. This is a y-intercept at negative 1. 1, 2, 3 up, 1 to the right is a slope of 3. So we did it. This is the algebraic way to do it, and to the right is the graphical way. Okay, so now the difference. So let's paste our graph again so you have the, so you have the numbers to refer to again. So again, here, if we label this at, I want to use black. So 10, this is our x. Now this is f minus g at x. So here we go. If I subtract the y values when x is 0, 0 minus negative 1 gives me positive 1. If I subtract these y values, at x is 1, I would get 2 minus 0, which is, so this is at 1, I would get 2. If I subtract the y values when x is 3, I would have 6 minus 2, which is 4. So this would be my graph of the difference between the two. And if you wrote this out, you'd have your f at x minus g at x. Do the g at x blue. This would give us, so f at x was our 2x, and then g at x was our x minus 1. So we'd have 2x minus x is x, negative negative 1 is plus 1. So f minus g at x yields these values. Let's check it out. So we had an intercept at 0, 1, that checks out, and a slope of 1, and that checks out. So we're good to go. Okay, so now the product and the quotients are a little different. So let's go ahead and graph those on our graphing calculators. All right, so I'm going to go ahead and graph all three. So if we go to our y equals menu, we'll clear this. So y1 is f, which was 2x. y2 was x minus 1. And then y3 is going to be two x times x minus 1. First one, second one, third one. Pretty cool, huh? So let me copy these for you. So the green is our first guy, which was what, 2x? I think it's this one. And then our blue one was x minus 1, which is this guy. And then the combination, the product, is this purple one. So FG is the product. So if we work this out, this would be quantity 2x times quantity x minus 1. So if you multiply this out, we would have 2x squared minus 2x, which is a parabola, and you see it there. So if you were to take specific, it's hard to see those specific input values, but you could really do the same thing. It would just be more difficult because it was a curve instead of a line as a result. Okay, so now let's do the same thing, but we're going to do the quotient. So the quotient is, we can go to our y equals screen and just change the operation here to divided by, and then graph it. And so that straight line that you saw represents a vertical asymptote, which we'll be learning more about. So this is our vertical asymptote, right? This here, this one was our green graph from before. This was our blue graph. Oops. Okay. Our blue graph from before. And then the new one is this one here. Nope, I overshot. All right, so we'll have, if we worked it out, we would have, this would be equivalent to f of x divided by g at x. So our f at x was 2x and our g at x was x minus 1. So we would want to give this caveat that x could not equal to 1. All right? And that's the result from the quotient. So here we go. Here is everything in one spot. So let f and g be two functions. The sum, f plus g. The difference, f minus g. The product, fg. And the quotient, f divided by g, are functions whose domains are the set of all real numbers in common to the domains of f and g. So the sum, as we wrote before, f plus g at x is equal to f at x plus g at x. The difference, f minus g at x, is f at x minus g at x. The product, fg at x, is f at x times g at x. And the quotient, f divided by g at x, is equal to f at x divided by g at x, provided, of course, that g at x is not equal to 0, because that will yield an undefined quantity. So here we go. We have new functions. Let's look at the sums. So first we get the sum in general, and then we get a couple examples where we have the sum at a specific value, and we do the same thing with the product. So f plus g at x will be f at x plus g at x. Well, f at x is equal to x squared plus 4x, and g at x is 2 minus x. So if we were to highlight, f at x is this, and g at x is this. So we have our sum. So we will get a result of x squared plus 3x plus 2 is our result for this sum. Now, f plus g at 4, instead of going through all that work again, why don't we evaluate the function we found at 4? So we'll just plug in a 4 into the sum function wherever we see an x. So we'll get 16 plus 12 plus 2, which is 30. So f plus g at 4 is equal to these things here. At the end of the day, we get 30 as a result. Now, this one's a wee bit tricky. This is equivalent to what? Good, f plus g at -3. So again, we use our function we found up here, and we say, oh, that's going to be -3 squared plus 3 times -3 plus 2, which is -9 minus 9, positive 9 rather, minus 9 plus 2, which gives us an end result of 2. Now we're going to go and we're going to say do the same things with the product. So we'll find our general product. So we'll have, this is equivalent to f at x times g at x, but f at x was our x squared plus 4x, and then g at x was 2 minus x. So we'll have, this is equivalent to 2x squared minus x cubed plus 8x minus 4x squared, which is negative x cubed minus 2x squared plus 8x. And this is our FG at x, the product at x is equal to these things. And so we'll box our result. Now, if we want to know the result of the product of these functions when x is 3, we would just merely say negative 3 squared minus, or 3 cubed, my apologies. I'll erase that. 3 cubed minus 2 times 3 squared plus 8 times 3, using the function we found, which is negative 27 minus 18 plus 24, which yields a result of negative 21. And so this is the product function evaluated at 3. Okay, now we are asked to find the domain of f divided by g at x. So why don't we see what the function looks like, right? So here, f over g at x is going to be f at x divided by g at x, which is f at x was our, looking back up here, x squared plus 4x, and g at x was 2 minus x. So basically, we'll have this quotient is this result, right? So we have to think about, what values of x are not okay. Do you see that 2 minus x cannot be equal to 0? So x cannot be equal to 2. So in set builder, we would have x such that x is not equal to 2. And in interval notation, we would say minus infinity to 2, union 2 to infinity. That will be our domain. All right. So that wraps up the first section of Chapter 2. Have a fabulous night. I, for one, am going to bed. It's way too late for this kid. So you guys have a fabulous night or morning or afternoon, and I will be talking to you soon. Bye.